at resonance, we could think of, even away from resonance, we could think of this transformer with that model we just developed on page 11. So let's take a quick look back at this on page 11. In this transistor circuit, this node is hooked up to the 9-volt power supply. So for AC, that would look like a short circuit. And so this part of the transformer is really just floating, and this is hooked up to the collector of transistor 9. So at resonance, these two would cancel, and all I would see is this value of whatever the load was on the secondary side of the transformer times the ratio of L2 to L3. Let's use that as an equivalent circuit. We'll resonate these two for right now and treat them as an open circuit, but all you see is this part of the transformer reflected impedance. So if we go to this page then, for AC, this will be a short circuit. This will be a short circuit, so these will get shorted out. Just have this voltage source and resistance here. In the actual radio, there was a smaller value of capacitance here. I think you need to increase that capacitance by at least a factor of 10 or 20. The value's on the bottom of the page. So this does look like a short circuit for AC. So in my analysis, I'm going to do that, and then you can think about how this impacts, or even do the simulation with that replaced, with the value you actually have in the radio. Now as far as the load goes, back out here, like I said, this is feeding the stage we just analyzed, the AM detector, and I'm just going to treat this as a couple hundred ohms. Then, with this being a short, then what I've got here is equivalent L and C in parallel, which I've picked to resonate at 455 kilohertz, and then all you see is this load reflected. So on page 13, then our equivalent circuit would be the transistors R pi and GM V pi, and then the resonated load, which is the load on the secondary side of the transformer times the ratio of L2 to L3. The output voltage here would be this current flowing through here, and that would create a drop in this direction, so we'd get a negative voltage relative to this point of GM9, R load, L2 over L3 times node voltage 22, which is the value of V pi 9. And then the voltage at the output of the transformer would be the square root of their inductor ratio times the voltage, in this case, between here and ground. Now, if the load were 200 ohms, and this again is going to not exactly be the value we get in our radio, but just something in that neighborhood, and I measured the values of the inductances on the transformer, and I figured out the dots using supplemental problem 1.19. So using these values with my value of GM, I'd predict a gain of about 101 out of this amplifier stage. And what would show up at the output of the transformer would be a little bit of a step down of that to a gain of 43.3. Let's see how close we come if we were to simulate this in SPICE. Again, using an ideal transformer with the coupling coefficients of 1. And these are the values of the inductance I roughly measured from the transformer, and also the capacitance across the input terminals. I plotted the voltage across node 21 and the current through it, which would give me the impedance really looking back through the transformer. You can see here that it has a value that peaks at 455 kilohertz with a value of 1090. Now that is exactly what was calculated right here. That was the value of R load times L2 over L3. In other words, 200 ohms, and then the value of inductance here of 163.5 microhenries and 30 microhenries. So it came out exactly as we had said. And so that approximation does seem to work as to how this transformer is working in this particular amplifier. We are getting a bandpass effect from the resonance of the parallel L and C. Then measuring the voltage gain, we had hand calculated a value on the previous page. I'm just going to measure it here as node voltage 21 divided by 22. Get a value about 87 for the magnitude, and then at the output of the transformer 37.3. We had hand calculated about 101 in magnitude and 43.3. So kind of the question is, well, why aren't they the same, or why aren't they exactly the same? Well, I use a certain value of biasing, assuming a beta of the transistor, but using the SPICE model for the 3904 transistor, that's just included in the PSpice library. We're going to be slightly off or away from that. So if we take a look at the value of GM calculated, the 82.7 millimos. So we had estimated it with our biasing to be 93 millimos. So pretty close, but not exactly that value. But if we go back and put that value in, the gain would be predicted around 90.1 and minus 38.6. And that's pretty close to the values that we'd measured on the previous page. If we actually also included the value of RO, which is 36.9K, it has about a 2 or 3% effect on the total resistance. But if we do include that, you get very close to the simulated values. These would drop by 2%. And that would get us pretty close to what we simulated in the previous results. So that's roughly how that transformer is working. Part of the transformer is only being used. It's really the center tap to one of the ends. The stage that's feeding the second IF amplifier, again this was a bandpass filter, is another bandpass filter, so we're getting like a doubling effect. And so again, what this transformer is doing is that these two coils are giving us the voltage gain for the transformer, and then effectively a reflected load here and a breaking up of this capacitance as some parallel equivalent circuit. So it allows you to, when you're tuning the transformer, you're adjusting the value of L. The value of C is just fixed there. You're able to tune it to a particular frequency, in our case 455 kilohertz for the AM radio. Here too I yanked this out, and this stage feeding the second IF amplifier, which has a differential input. And so I'll show as a resistance back to ground and back to ground. What's biasing this amplifier is the output of the automatic gain control circuit. So let me just put a fixed battery here, and then I'll vary this and we can see how the performance of the circuit varies. Here too, again, I've got to maybe approximate the DC and AC results so that I can get a rough handle on what the gain might be. And we can run SPICE again and see how close we are using the same models. And then of course we could take and put in more detail and see how close we come to the actual measurements. If this is 1.5 volts, then this node voltage here, if this is a fairly small resistance and then the base current is small, would be about the same potential. Again, this is an AC source. The output of transformer 6. So then this node voltage here would be roughly 0.7 below this one, or about 0.8 volts. And then divide that by 1K and you got about 800 microamps. So this transistor's emitter is biased at 800 microamps, a little different than the previous case, and that makes the collector current about the same size. So we could then calculate the value of GM. In this case it'd be around 30 millimos. The value of our pi, again assuming 150 for the AC beta, gives about 4.8K. Maybe we should include the value of RO with our transistor. The 3904 has a VAF of 74 volts if you look at the SPICE model, and the collector currents are around 800 microamps. So you get about 92.5K. Here too again, the actual radio used a value of 0.02 microfarads, and I found that you really need to have a much larger value here to have this look like a short circuit at 455 kilohertz. Here too again, at resonance, we're going to have this top half of the circuit literally disconnected from the bottom because of this short circuit here. We're going to represent this capacitor as two capacitors, then we'll have a parallel resonant circuit. Whatever voltage is here is then stepped down and shown up over here by the square root of the inductor ratio. Let's calculate those things and see how things come out this time, but we'll include RO. It does have a much bigger effect this time. So here I've got two resistances back to ground. They form a single resistance across the secondary of the transformer. And again, that's going to be reflected by the ratio of L2 over L3. Okay, then that in parallel with the RO of the transistor forms a parallel combination, and this current then all flows into that combination in that direction. And so I get a negative gain again. Then the voltage across the differential output will be this node voltage times the ratio of L3 to L2 square root. So if I were to have 1.6K on the secondary side of the transformer and a 1 ohm resistor, and if L2 were 55 microhenries and L3 were 3 microhenries, and these were about the values I measured on the transformer when I was tuning it for 455. I would predict a voltage gain then of the GM, and then I've got a created impedance of about 29.5K, and that's going to be in parallel with RO of transistor 8. So we get a much bigger gain out of this stage of 689. Again, it would be negative. Magnitude would just be the 689. And then the transformer would step that down to about a gain of 161. So this is going to then be past the second IF amplifier. It will be filtered again and amplified. So we'll be able to get enough gain to be able to hear our received signal. Once again, let's verify this with PSpice, but using the model for the 3904. We'll take a look at this in a narrow band of frequencies around 455 kilohertz. Here can now plot the voltage at the collector divided by the collector current, and I predict about 29.533 kiloohms. This is virtually identical to the value of the resistive load multiplied by the inductor ratio. The voltage gain, about 723, so pretty close to the value predicted of 689. And then the gain at the output of the transformer differentially to node 32 is 169 in magnitude. We predicted 161. I also measured the Q of the filter. It was around 146, taking the center frequency and then dividing it by the difference of the two 3 dB frequencies. I could also roughly calculate this. We have a parallel resonant circuit. The value of R is going to be the reflected resistance, and then we have a parallel resistance with RO. The value of C2 is the value of C0 multiplied by 1 plus the inductor ratio, and then divided by L2. That gives us about 109, so we're kind of in the ballpark with the value of Q0. Now if we include the actual value of GM and RO, you can see how close we come to the predicted gains. So GM is actually 31.9 millimos in this particular case, and we had estimated or calculated as 30.77, so pretty close. Just a rough approximation with the voltages we had. The value of RO we had predicted to be 92.5 k-ohms, so pretty close. But if we include these values in here now, we predict a gain of 723 and 169, so almost identical to what we had in the simulation. So in recap then, we've got two bandpass filters, both with fairly high values of Q. You see the sharpness in the filter, and also quite a bit of gain. So we're going to be passing the received signal after it's been mixed down through two bandpass filters, just letting the 455 kilohertz signal through, and hopefully rejecting the nearest radio station that's been mixed in with it.